has a dipole. Which direction is pulling the electrons? Towards the Cl. So there's our dipole. Because there's no other dipole to counteract this one, this has a net dipole. And I'll get into net dipoles. It has a net dipole, therefore it's polar. It's a polar molecule as well. So HCl is a polar molecule and it contains polar bonds. Here's our Lewis structure for H2O. Or here's our Lewis structure for H2O. A lot of times you will see me draw it like this. It's like that V shape. Okay, it's like that V shape. When we get into grade 12 chemistry, we will actually be talking about shapes. Lone pairs of electrons actually take up more space than bonding pairs of electrons. So instead of sticking out here, those hydrogens are pushed down by the lone electron pairs, which is why it ends up in a V shape. Okay, so structural diagram. If you want, you can do this. I will be doing this. I'll accept either one. So there's your structural formula. It's a good habit to get into. If you know the shape, to draw the shape. And then the name, of course, is or dihydrogen oxide or monoxide. AKA water. So the shape of the molecule with the electronegativity difference between the two atoms determines whether a molecule is polar. If water had a linear shape, like that CO2 molecule we did, it would be nonpolar. Water is bent in shape and is polar. So you've got two dipoles. You've got a dipole going towards oxygen, because oxygen is higher. So you end up with a net dipole. For those of you that took physics, when you add vectors, you've got a tail and you've got a head. The head of the first vector goes to the tail of the second vector. So my second vector would go this way. Am I back where I started? No. So I have a net dipole. And your net dipole goes from the tail of your first one to the head of your last one. So here's my net dipole. Okay. CO2 Lewis structure. So carbon has 4 valence electrons. It needs another 4. It only has 2 atoms, so it's going to get 2 from each one of those atoms. So CO2 Lewis structure is going to look like this. We can actually connect those dots and represent them as double bonds. So your Lewis structure could look like either one of those. You can see that the one on the right with the actual bonds is a little neater. Now you do have to be careful that you don't have stray dots on your page when you're doing these, because I'll think you've just thrown in an extra electron. So structural formula shows no lone pairs of electrons. So it just shows the bonds And then this, of course, is carbon dioxide. Here, our dipoles go in opposite directions, but because they're equal and opposite in directions, when you add these two together, you end up back where you started. So there's no net dipole. Therefore, the molecule itself is nonpolar. Okay, so it's a nonpolar dipole. I mean, a nonpolar molecule. No net dipole. All right, so in general, covalent compounds do not conduct electricity. Therefore, they're non-electrolytes. Low melting and low boiling points. So that indicates there's very weak forces of attraction between the molecules. And we're going to get into what those are in a little bit. They evaporate readily. So if you leave a beaker of water out, eventually, it's gone, right? It just disappears. It evaporates. And that's because of these weak forces of attraction. Isopropyl alcohol or rubbing alcohol does it even faster. And we talked about mothballs. They're solid. They evaporate too, yeah?
Is that what, do you know how there's like alcohol pads? If you leave it on for like 5 minutes or something, they get like super dry?
Yeah, because all the alcohol is evaporating in the air.
Oh, that's cool.
Yeah, so they dry out. And they get like that too if they're quite old, because it just seeps through the wrapper, or maybe there's a hole in it. Yeah. So many are not soluble in polar substances like water, but are soluble in nonpolar solvents. So if you are nonpolar, you can dissolve in another nonpolar liquid. And if you're polar, you can dissolve in a polar liquid like water. Smaller molecules are more likely to dissolve in water than large ones, and solids are usually soft. It has 5 valence electrons, so 1, 2, 3, 4, and then double up. How many total does nitrogen want?
8.
So how many does it need? 3 more, so it bonds, makes 3 bonds. Oxygen. Lewis structure for oxygen. 1, 2, 3, 4, 5, 6. How many total does oxygen want? 8. Geez, see a pattern here? 8. So how many is it short? So it makes 2 bonds. Hydrogen is an exception. We'll put it off to the side for a minute. Fluorine. 7. So how many bonds? 1. Because it wants 8 in total. So chlorine, bromine, and iodine, same column as fluorine. So their Lewis structures will look the same. They will make 1 bond, right? Hydrogen has only 1 valence electron, but how many total does it really want? 2. So it actually makes only 1 bond. So hydrogen will never be put in the middle of a structure. It will always be a terminal atom, right? Always on the outside, never on the inside.
Because it has 1, you can't connect it with more than 1 place.
Exactly. I can't tell you how many times I see somebody write water like that. You say that? Who's going to do it? Okay. You're going to do it?
Oh, no, I have a question.
Okay, so because there's only 1 bond, How about H2O2?
Please report to student service.
2. So if oxygen wants to make 2 bonds, where am I going to put my H's? Terminals. There you go. Nice. H2O2. How about C2H4? I've got 2 carbons, 4 hydrogens. Which ones do you think go in the middle? Carbons. So let's put our carbons in the middle. Let's put 1 bond between them so we know they're connected. 4 hydrogens. Do you think 3 and 1, or do you think 2 and 2? So let's see what happens when we put 2 and 2. So 2 H's, 2 H's. How many carbons, how many bonds on each carbon? 3, right? Right now, 3. How many do they make? Yeah. You said it, Archie. Say it louder. Need a double in the middle. If we did it the other way and we said 3 H's, this second carbon would not be able to fill its octet because the other carbon can't make any more bonds to it. So we know that that one's wrong.